end a lot of suffering in the world. So we're talking a little bit about MitoSENS tonight, and I'm just going to give you my layman's understanding a little bit here for background for people, what I know about MitoSENS. You're the expert, and we'll get into more detail, but mitochondria DNA undergo mutations or damage throughout your life, and they become debilitated as you get older. And one way to protect mitochondrial DNA from getting damaged, which it does seem to get more damaged than nuclear DNA, is to take those mitochondrial DNA and put them in the nucleus where they will be more protected from damage. And that's, in a nutshell, the MitoSENS program. And could you maybe elaborate a little bit on that, or did I cover it pretty well?
Yeah, that's the basic idea. I guess MitoSense definitely is concerned with obviating the effect of mitochondrial DNA mutations. And although we focus on the idea of moving the mitochondrial genes to actually sort of replicating the mitochondrial genes in the nucleus using gene therapy, we are open to a number of other methods that exist with the idea of obviating mitochondrial DNA mutations. But right now, yeah, we are focusing on allotopic expression is the term for transferring those genes to the nucleus.
Now, and the thing is, the one thing that struck me is that seems like a pretty radical therapy to protect mitochondrial DNA. Just moving, hey, let's just take some of these, let's take some of these genes and just move them to a different part of the cell. It would seem something difficult to do, but apparently this has been done in mice, something called protofection.
Protofection's actually a different technology entirely, and it's one that we're also interested in. Actually, I'm currently talking with the protofection people about independently reproducing their results in our Paris lab right now.
Oh, okay. Explain it to me. Correct my misinformation here as far as protofection goes, and how it relates to MitoSENS.
Yeah, so protofection is the idea of actually, instead of transferring the mitochondrial genes to the nucleus where they'll be more protected, and the other advantage is that we actually have gene therapy for the nucleus. We don't have gene therapy for the mitochondria, so it's that's part
because
of the reason
it's more difficult to get therapy into the mitochondria than it is to get it into the nucleus.
Well, up until protofection came about, nobody had done it before, and the only people that have done gene therapy in the mitochondria still are the protofection people. But the thing is that so their technology is to actually take entire mitochondrial genomes, coat them with a proprietary protein sort of coat that they've developed, and then inject that as a vector that will actually be specifically taken up by the mitochondria and will replace old mitochondrial DNA. And so what you would do is periodically replace damaged mitochondrial DNA with fresh copies delivered as a vector.
Okay.
And so their technology is it's quite conceptually, it's simple and it makes a lot of sense. But they've had this for a long time.
How long?
And they seem to be, I think 10 years now, maybe, since they first came up with it. And they've been making very slow progress. They've had publications and they've given talks, and they make it sound incredibly easy. But if it's so easy, why has it taken them this long to actually make any progress?
Yeah.
So it seems like it's not. It seems like they're selling it as being easy when it's probably not as easy as they say it is.
Okay.
And so I'm looking forward to actually collaborating with them to find out what the actual limitations of this method are.
Because it's been done in mice, right? Apparently they've had positive results in mice.
They say, but they don't publish any of their methods. They only publish the results. And so, I mean, you like to take people at their word, but you have to, in science, you have to be skeptical. I mean, you have a snake oil segment, so you know.
Yeah, there you go. The Harmony chip in the snake oil segment. Yes, tonight. And that is our first viewer question, in fact, for tonight. Do you foresee anti-aging therapies based on mitochondrial protofection. Now, you said, hey, you haven't really been able to see the methods yet, right? So maybe that you really can't answer that question, but I mean, it does seem like something that could be used in humans. I mean, if it works
Yeah,
as elegantly as what the people say who discovered it, who developed it,
yeah, it's promising in principle, and so we're looking at we're supporting a number of different areas. So basically our strategy is, since we don't know for sure what the best method will turn out to be, we don't want to put all our eggs in one basket. And we're supporting allotopic expression right now because it seems to be the most where we can sort of affect the most leverage in terms of the research. But
okay.
yes, we're certainly if protofection does turn out to work well, then allotopic expression won't be necessary, and that'll be a good thing.
Yeah, because would you say allotopic expression is a little bit more advanced or technical or difficult than would be
I think,
protofection?
yeah, allotopic expression is extremely difficult. In fact, out of the different SENS strands, the only aspect that's more difficult is the cancer area.
Wilt,
Yeah,
the
wilt,
wilt.
which
Okay.
obviously has a lot of reasons to be skeptical about that. So I think allotopic expression is it's not that difficult, but it is very difficult.
Okay, but
And
it
yeah,
has
I just
been.
see.
Okay, it
Well,
has.
yeah, I see.
Okay, go ahead. Go ahead.
Oh no, yeah, I just was jumping in because I saw the question came up there that it has been done. So people I guess there's been a number of reports over the years. Allotopic expression is something people have been working on for 20 years now, and there
20?
have been a couple. Yeah, it's been going on for a long time, and so the thing is, there's been quite a few false positives. There's been a lot of people that have said, yes, look, we've got it working, look at our publication, and then multiple labs have been unable to reproduce the result, and that's happened a number of times. So just because there's a
Mm.
paper that comes out that says we've done allotopic expression, because there's been so many false positives in the past, you can't really take their word for it, because it is such a difficult thing to do,
Yeah. You
and
got
even
your
if you
work cut
do
out
get it
for you.
working temporarily, if you get it working in one very specific system, it may not work in any other system. And in order to be a therapy, it needs to be more, better, more generally applicable, and more
Sure.
safe, and such.
Yeah, now I remember a couple of discussions in the Immortality Institute forums a couple of years back about allotopic expression and putting different genes into the nucleus, and perhaps that there could be some problems with that. What type of uh, things can you foresee that could be stumbling blocks? Say you are able to transfer those genes into the nucleus. What type of side effects or problems might occur by introducing those new genes into the nucleus? Or is it just something that, hey, they go in there, it's fine, the cell operates just like normal, the correct proteins are made and they go to the mitochondria or whatever is going on in there. But what type of things? There's some people I know that have argued that there might be some significant side effects.
There has been, and that's one of the reasons why a lot of the previous approaches to allotopic expression before the lab that I'm in now started working on it were very crude, and they didn't really look like the advantage to allotopic expression is that most of the proteins in the mitochondria are already encoded by the nucleus. So our
Oh yeah,
cells
well,
have the machine.
there's like a couple of
Yeah,
thousand, aren't there, that are
yeah,
already
between
encoded?
3,000, 3 to 5,000 genes.
Okay.
And so, yeah, I mean, the cell is already very good at doing this. The thing is, we need to properly mimic all of the different elements that are necessary in order to achieve it. And in the past, what people did was they just took a mitochondrial gene, they changed the codons from the mitochondria to the nuclear codon set, put it next to a powerful CMV promoter, and just expressed it and at a very high level with no other regulatory elements. And that turned out to be a very efficient way of killing cells because the proteins weren't efficiently incorporated into or taken into the mitochondria, so they would aggregate and they were also being expressed at levels that were probably much too high.
Huh.
And they're very hydrophobic proteins, so they would just aggregate and the cells would die.
Okay.
That's the interpretation.
Hmm.
And also some mitochondrial genes. I
Hello?
lost you there. Can you
Oh,
hear me?
I think we're back. Can you hear me? I'm sorry.